Okay, I think we can get started. Thanks for coming. So I'm going to be talking about developing music creation apps for the web, desktop, and for Android. So my name is Phil Burk, and just to give you an idea of sort of what led me to doing this, what my motivations were, give a quick timeline for my involvement with music and computer music. So back in the 80s, I was building analog synthesizers in a shoebox with springs to make the connectors. It was very cheap. I had no money. And then after that, started building digital oscillators, digital waveform generators. Then developed a computer music language called HMSL, which I'll mention again in a second. Then moved to a video game company called 3DO, where I developed a DSP-based audio game engine. And then developed the WebDrum in sort of the late 90s. I'll be demonstrating a new version of that. Also worked on KSyn and Port Audio. Port Audio is a cross-platform audio library written in C. Then later worked on the Sony PS3 audio and worked on the MIDI 2.0 specification. There's a new standard for MIDI. After 30, 40 years, there's now a MIDI 2.0. And then worked at Android for about 12 years, developing new native APIs for high performance, low latency audio called A-Audio and Oboe. So that's sort of the journey, and led me to working on these projects. So the things I'll talk about is a little bit of history of cross-platform, multi-platform music coding, why I moved my projects to Kotlin. I'll give a demo of WebDrum, the new WebDrum. Introduce a multi-platform audio API that's available now. I'll talk about Kotlin techniques and issues involving real-time music and kind of the things you have to watch out for, and discuss some solutions for networking for multiplayer apps. And then I'll give another demo for Praxinista, which is a kind of a music practice app, and then talk about this new KSyn synthesizer, which is a software synthesizer library in Kotlin, of course. So back in the day, I was writing a cross-platform music language called HMSL, and it was an experimental music language that was running on Mac and Amiga. And in order to be able to move code back and forth between these systems, we had a cross-platform library of about 20 functions to open windows, draw lines, draw text, output MIDI, input MIDI, and so forth. And using those, you could write an interactive GUI-based music program and then port it back and forth between the Mac and the Amiga. So it was kind of an early cross-platform system. The person in the middle of the screen there is Larry Polanski, who was my partner on that. And one problem that we realized fairly early on is that when people go to concerts, if they go to a concert with someone playing guitar or maybe violin, you can see the musician, you can see what they're doing, and then the sound comes out and it makes sense. You know that if their fingers are moving quickly, you're going to hear a lot of notes. But in a computer music concert, there's someone sitting like this behind a screen, and they're clicking madly on a mouse, and there's all these notes coming out, and the audience is thinking, what's happening here? I have no idea what I'm hearing and how that relates to the audience. Larry would try to jazz it up. When he would click on the mouse, he would make these grand gestures to make it, sort of make it a little more performant. But the audience still never really had as much fun as we did. Whoever was on stage was having more fun than the people in the audience. So we figured, okay, what we need to do is allow the audience to be the performer. So created this a KSyn synthesizer, which is a modular software synth in Java. And you could put applets on the web. And so then people could the audience, could log into a website and they could perform the piece. They could play with the buttons. They could move the knobs, and they would hear the sound and they go, "Oh, okay. When I move this fader, it gets more dissonant or higher note density or something." So that worked fine for a while. And we were able to do things like this WebDrum interactive app that would run on the web. And but then in 2015, Doom, Chrome dropped support for applets. All the other browsers followed suit. Apparently Java was had security issues. It was a powerful language running in the middle of your browser, and it was constantly under attack. So all the work we did for providing cross-platform Java applications on the web, we could no longer do that. So I figured we needed a solution. 10 years later, Kotlin and Compose comes to the rescue. So you all know about this. The multi-platform Kotlin runs on the web, desktop, Android, iOS. Everything is great, so I started moving all my code to Kotlin, really loving the language. Got rid of those pesky semicolons, and plus lots of other new functions. And but I couldn't find the audio library, and I contacted JetBrains, and they asked if they had anything in the works. Were they planning any audio APIs? And they weren't. So I figured I better roll my own. So in order to do real-time music with Kotlin Multiplatform, I needed two things. One was an audio output library, and the other was a synthesizer, something to be able to make sound. So I figured one of the first things I should try to do is try to recreate this WebDrum from the 90s because it was really one of the first multiplayer online systems for that was on the web. I see someone had a BandLab T-shirt. There's new systems out now that are full DAWs on the web, and it's amazing. But this was sort of the first kind of primitive app. So what it did, you could have multiple clients, the green boxes, and they could communicate with a room running on hosted on a TransJam server, which was just a Java server, and running at TCP connections. And everybody in the same room could hear each other performing on this drum jam. So I'll just give a quick demo of that. So on this transjam.com website, you can do this yourself. I'll just it's your basic drum pattern editor. If someone else was logged in here at the time, they might grab the snare drum, and then they could be editing the snare drum. I might be editing this other instrument, and the sounds that are being synthesized are mostly not samples, so they're being synthetically generated using this, now the KSyn library. So you can get some pretty strange sounds, like here's a plucked gong, which is a Karplus-Strong algorithm. So you can get the idea. And you can do polyrhythms, like you could do something in a certain number of notes and 6 beats, and you can do just intonation, pentatonic just intonation, and so on. And other people might log in, and they might, some be controlling the tempo, someone might be controlling some other melody, other people controlling different instruments. So it's allowed people in different parts of the world to log in together and jam together and make music together. So it's a lot of fun. So So that's at transjam.com if you try that later. So, this also runs now on Android. You'll notice that the API on Android looks, essentially identical. Some things were a little bit different. So on Android, when people scroll, they're not like typically grabbing a scroll bar and moving it, a contrary motion. Where if you move up, the screen will move down as opposite the scroll bar. That's a bit unnatural on Android. Android people like to grab something and move it around, push it around. So you can do two-finger drag if you click, if you on in certain areas. And then there's a little custom drag bar on the side, so you can click that and then drag that up and down and move, move the full screen to access all the different drums on the smaller Android screen. So it worked pretty much the same, but there are sometimes just little differences in the user's expectations about the way that the UI will work on desktop versus on Android. And even though we could implement it the same, the users wouldn't necessarily be comfortable with that. So this was a screenshot in case the demo didn't work, but it did. Yay! So one of the big things that required to do this was to have some way to get sound out of the system. So created this thing called the KSyn audio bridge, and what it does, it uses the expect and actual class definition. So if you haven't used it, expect and actual, it's kind of like an interface, but instead of implementing the interface with something that's like a new class or something, you've got an expect, which defines what that class is supposed to do, but it doesn't do it. And then there has to be an actual class that then implements what that expect class is. So it does behave differently than an interface and subclasses. So the application calls the API of the audio bridge, and then there's 3 different implementations currently, one for desktop, for WASM, and for Android. So this is open source, and it's not currently on Maven, but if you clone the GitHub repo, and then there's a Gradle target that will publish to your local Maven, and then you can just pull that into your other project and do output. So it's very easy to use. So this is basically all you need to do to output sound. If you want to output interactive sound from your app, you create an audio bridge, an output in this case. You open it, which will grab the resources, audio resources. You'll need to run kind of under a coroutine, so that while this audio coroutine is running, you're also doing your AI and your other activities. Start the audio bridge, and then in a loop, you just render your data somehow into an audio buffer using your own synthesizer or the KSyn, and then you just write to this suspend function, which will block until the data has been written, and then keep doing that until the user shuts it down. So it's very simple to get audio output. On the back end, in the actual classes, there had to be different implementations for different platforms. So for the JVM for desktop, it's using the Java Sound API, which is pretty simple to use. I just had to take the float data, convert it to short, and then convert that to a byte array, and then output a byte array to Java Sound. On Android, it was even easier because there's an audio track write function that will take a float array directly. It has a blocking mode. So this was pretty straightforward on Android. On the web, not so easy. WebAudio has a great audio worklet node, which lets you run JavaScript as high priority under a low latency, special audio thread. But it can't call back up into Kotlin, and it's difficult to, so we couldn't run the Kotlin code there. So what we do is set up a FIFO, and the audio worklet is just reading data from the FIFO as fast as it can, or as fast as the audio pulls it. And then the the application is just writing into this FIFO ahead of the audio worklet node. So to implement the FIFO, so it's an atomic FIFO because there's just a frames written and a frames read. So those two variables control where you are in the FIFO, and as long as only one process is updating each one, so the application updates the number of frames written and the WebAudio worklet updates the frames read, then it will be atomic. So the hard part in this one was setting up these shared array buffers. So there's one shared array buffer which is sort of wrapped as a float array, and that's used for the audio samples. So we're writing the data into that. The other array is a int32 array, and that's used for containing the indexes, or sort of frames written, frames read, for storing that information and then being able to pass that and make it visible, between the two processes. So here's an example in the callback code, using atomics to load this value from the shared integer array. And then we can, write some data, or I'm sorry, we'll grab some data from the shared float array at that index, and then, we can update the frames read cursor, and then that's visible to the other side. So it is done in blocks. So this is a simplified version of it. So we need to use the JavaScript atomics in order to make this work. So as soon as you start using something like a shared array buffer, the browsers will complain, and it'll probably throw an exception initially, and you'll get, if you open up the JavaScript console, you'll see things like shared array buffer used. It doesn't say why that's bad, but it gives you a clue that that's what's gone wrong. And so you have to tell the browser that you're intentionally using this shared array buffer, and to allow this sort of cross-origin. I don't fully understand what the browser is complaining about here, but by specifying this .htaccess file and just putting this with your web app, you can allow this cross-origin activity. So you've got these two processes communicating in the browser. That's fine if you control your own browser. This will work as is, like for Apache. But if you're using something like GitHub, it's a purely static website, and you can't configure the web server. The web server is GitHub, and you don't have access to that. And so there's something called this COI service worker by Guido Zwidoff, and you just need to put this script next to your WebAssembly code, and then invoke that script, and it will set up the headers, and it'll work just fine. So without this, it won't work. So for the future, for KC Audio Bridge, the API may change. Get a few more people using it and banging on it. So it's probably not going to change, but it might. And I'm also looking at maybe adding native desktop support for when Kotlin compiles to native, and using the port audio C API to access the native APIs on the device. I also want to get the iOS stuff working. I've not done much iOS development. If someone has and wants to offer some advice on that, I'd be very happy to hear that. Audio input, I would love to do, because you can really do some fun things with processing sound, but that is another level of complication in terms of security. So what other changes were needed to make all this work? So unlike on Android and on desktop, you have a fair bit of freedom, moving between those two platforms. You can use a lot of the JDK APIs. You can use Java threads. You can do all kinds of things that are the same. There's no swing, obviously, but as soon as you go to WASM, a lot of the things that you were able to do on Android and desktop don't work, and it will not compile. So you have to avoid using the JDK APIs. There's no thread class, so everything has to be done under coroutines. There's no reflection. And then for the networking, there are the regular Java I/O socket, networking I/O stuff doesn't work, but ktor does work, and I was able to use that to implement the WebDrum. So also, I'll talk more about networking. Also, just your basic I/O exceptions, your Java are not implemented, so you need to implement your own exception classes that are subclassed from the basic exception. So not hard. So the coroutines I found interesting because it was kind of a flashback. The Java threads are sort of true threads. They will do preemptive, they can preemptively interrupt one task and switch context to another task. And they can run, on multiple cores. That context switch can be a bit expensive, and it's a little bit dangerous if you're not properly synchronizing your data. But I was more used to working with a thread class. The coroutines are a little bit lighter weight because you're not doing a full context switch. It's faster, and it'll only switch at certain points. So when there's a delay, or if you call a yield, or you call a suspend function, then it may switch context to, suspend functions that call blocking functions or these delay or yield. So it only switches tasks at places where you would expect it to switch. And this kind of reminds me of the sort of multitask, or the cooperative multitasking on the original Apple devices. It is kind of a similar system. Currently for WASM, it's single core, but I mean, luckily single core is usually pretty fast and fast enough. So another issue I ran into, the WebDrum normally uses a TCP/IP connection. So this was written, the server was written in the late 90s. Now I would probably use some sort of a REST API or some sort of different interface. But I'm trying to use the original server, and it's expecting a TCP/IP connection. So on desktop and on Android, it's no problem. I can use NetBridge. I can do a TCP/IP connection to the Transgem server, and then when messages come in, I'm looking here, pointing, but you can't see this. But up there, when messages come in from the TCP/IP server, I convert those into stateflow messages, and then the stateflow migrates up to the UI. So if someone clicks on a drum, or they turn on a drum on their machine, you'll see the compose UI will update on the local machine because of these mutable stateflow messages that are sort of streaming up from the network interface. So that all works fine, but on the web, it was more complicated. ktor, the WASM cannot open TCP/IP sockets, but it can do WebSocket communication. So I used, what I did was use on the server, use ktor again, and in Kotlin, set up a WebSocket service on the running on my server, and so the application can open up a WebSocket interface to this relay point, and then it opens up a TCP/IP connection to the Transgem server. So it's getting WebSocket messages, and it just relays them right on to the Transgem server and then back. So it's just passing messages back and forth, and it surprisingly kind of worked just fine. I want to demo another different app. This one was, I've been playing guitar for 45 years, but I'm always trying to learn new things, and I like to be able to, practice different scales, or practice, switching pentatonic scales in different chord progressions, and sometimes play with backing tracks. But I wanted something that would show me on the fretboard sort of what is the which notes to play as the chords are changing, which notes to play and which notes not to play. So I wanted to be able to display a fretboard with pentatonic scales, and then also a piano keyboard. So this is implemented on the web, and so you can choose either guitar or keyboard. We'll keep it as guitar. You can set up a chord progression, change tempo, change how many measures per chord. So there's a lot of different options on chord progressions. You can do 12-bar blues or any amount of the sort of common chord progressions. And then when you start playing, it just plays this sort of simple backing chord track. I'm going to be adding some percussion and some things like that, but I also wanted the chords just to be easy to hear. And then you'll notice that the notes are changing. So for example, in this case, the 3 and the 4 is the main thing that's switching. So if you're jamming and you're trying to play between these two chords, you could try to think of like I'm switching between two pentatonic scales, but the easiest thing is just to think about, okay, right now, don't play the 3, the 3 note in the scale, and now don't play the 4 note. So you just have to think about one note at a time, which one you don't play. So you just sort of avoid that note and then play your pentatonic scale, and it's mostly the same except for those two notes. If I was throwing in the 5 chord, then the 7 and the 1. So what these mean is like, so the 1, if you're in the key of C, C is a 1, D is a 2, E is a 3, F is a 4, and the E and the F are right next to each other. And if you play those two notes, in that scale, it's going to sound dissonant, which may be great if that's what you want, but it may not be. So this gives you an idea of what, how to play anywhere on the fretboard. And then there's similarly, a keyboard one as well. So all of this was written, just Kotlin compose, just drawing into a canvas, and I found it very straightforward. So I think that Kotlin compose is, a good platform for get back to full screen. There we go. So I think Kotlin Compose, is a good platform for doing interactive music, assuming that you can get the audio out. So that was a key thing. A lot of people have their own synthesizers, but KSyn's available if not. So this shows Praxinista running on Android. The layout's a little different. I think I was using some kind of flow layout that would just sort of automatically adapt to the portrait or the landscape modes. And generally, I've found that between the web and desktop and Android, that the UI just looks identical. So quite happy with that. And that's if demo didn't work, but it did. Okay, so KSyn, I've referred to this a few times. KSyn is basically a modular synthesizer. So if you picture one of these giant modular, like a Moog or a Buchla or a Eurorack synthesizer, you've got all these modules like oscillators, filters, envelopes, and they all do different functions operating in the analog voltage domain. And then you connect between them with patch cords, and you turn a bunch of knobs, and you can make all kinds of really fun, crazy sounds, but you can spend a lot of money buying modules. And so it's a road you may not want to go down. But luckily with software synthesizers, you can, I think I'll instantiate 20 oscillators, and it doesn't cost anything. So it's a good way to go. So what I did, I wanted to port, I had this synthesizer written in Java, the JSyn, but there were a few things that I wanted to change in the API. I was passing doubles around, and I wanted to use floats and maybe take advantage of the SIMD code a bit more, and just have a little better performance. JSyn was really wedded to the Java Sound API. And so using the JSyn code as a spec, I ported, there's over 100 unit generators in there, so I ported some of the sort of key unit generators over as an example to see what needed to change when moving from Java JSyn to the Kotlin KSyn, and then just systematically using Gemini Pro said, okay, look at these examples using anti-gravity, and then look at the JSyn code, port the filters, just in groups we could port the stuff over, and I feel like I'm cheating a little bit to use agentic coding, but there are hundreds of files, and I just manually porting from one language to another. I probably wouldn't have done it, and it just feels like a good use of of agentic coding. So now it's running. So KSyn, it's free under an AOSP license. It's Kotlin Multiplatform compatible, which means that it will work on all the desktop and web and various platforms. This was the main motivation because I couldn't run JSyn on these platforms, and or at least not on WASM. KSyn now has no audio I/O. It's basically you put numbers in, parameters in, and you get numbers out. You get audio, blocks of audio PCM. So if you're just doing math, then you can be very portable in that case. And then we use the audio bridge to output the sound once you get it from KSyn. So in this library, there's, like I say, over 120 different types of unit generators, band-limited oscillators, which means that you can crank the frequency up and not get a lot of the digital grunge that you get if you're not real careful. There's resonant filters, low pass, high pass, band pass, Moog style filters. It's very flexible, segmented envelope and sample queuing library. So you can incorporate samples along with all the sort of analog style software synthesis. There's a granular synthesis feature, lots of effects, such reverb and wave folding, and even some spectral processing. So you can do IFFT and then do a spectral filter and then do the IFFT to get back to the audio domain. So there's a lot of stuff in there. So how would you use this? You can create there's more docs online, but you can create distribute it to Maven local, similar to the way you do with the audio bridge. And then in your application, you just create a synthesizer, which will give you, so your API is defined by the interface, so there are some other methods that are a little bit sort of hidden by using this approach. And then you can just start creating modules. So make a sawtooth oscillator that's band limited, and then just add these modules to your synthesizer. So for example, you may have a sawtooth oscillator connected to a low-pass filter with an envelope player that's controlling the amplitude, and then going to a line out. So the syntax is pretty straightforward. So you can see that if I want to connect the sawtooth, I take the sawtooth oscillator output and connect it to the low-pass filter input. So it's kind of readable, straight across. Sometimes it's easier to sort of map this out on paper and then make sure all the connections are there. We have a graphical patching system for JSyn, and eventually I'll port that to Kotlin as well. And then when you want to turn a knob, basically you want to set a parameter and change the frequency or change the cutoff, change the attack on an envelope. So you just, on the SAW frequency set to 440, which is a concert A. You can also set parameters in the future. So one of the things with real-time music is you want the timing to be really rock steady. But particularly on sort of slower processors, there can be scheduling jitter, there can be things happening at the same time, windows opening, and that will cause your execution to be a bit ragged in timing. And if you just are doing things now, immediately sort of at the time the code executes, you change the sound. That can mean that your notes might sound a little ragged in your timing. So what you can do is you can specify these changes just like maybe 100 milliseconds in the future. So there's still, fairly low latency, but if your scheduling jitter in your operating system is, say, 50 milliseconds, rather than having your notes bouncing around, you just schedule everything in the future, and then within the synthesizer, the events will occur at the right place in the audio stream. So you can still get, the kind of rock solid timing by scheduling things at the sort of composition time. So within your piece, you're thinking, I want this note to be at this time. It's not necessarily the wall clock time. It's where is it in the composition, and so you can just pass that in along with setting parameters, making connections, and you can also like send in a lambda, with a time that will do various things. So you can set a bunch of things all at once. You can also load samples. So, oh, is that me? Sorry. You can, for Kotlin Multiplatform has this, or Compose has this res function. So it's a way to access resources in a cross-platform way. So if you incorporate your samples into the app using as resources, then you can just grab, get a byte array of the contents of that sample file, and then you take a sample loader and you say load a float sample from this array of bytes, and then you've got a floating point sample that may be a clarinet. Then when you play it, we've got these variable rate readers. There's also fixed rate mono readers. But what you do is the sample player has the data queue, and so you can queue up pieces of the envelope or pieces of the sample. So often in a sample, picture like a clarinet, there's an attack, which is that sort of initial part of sound, and you want to queue that up. And then you want to queue some piece of the middle of the sample to play in a loop. So it'd be like, and that's actually a short piece of the sample that's just looping. And then when you want to release the note, you queue up the release. And you just queue that, and when it finishes the current sustain loop, it'll just go into the release. So you can queue an attack, sustain, release, which is the classic thing, or you can queue up like 20 different weird sounds that are all like, in sort of any arbitrary way. And you can also get callbacks when you reach certain points within as the queue gets processed. And so it's a very flexible system. You can also change the rate of the sample player. And if you set it to the recorded frame rate, it'll play it the way that it was recorded. So if it's a voice sample, you'd want to do that. But for a clarinet, we can make it sort of go up and down in pitch. And I'll demonstrate that. Envelopes are very similar. And they can use the same variable rate mono reader that we use for samples. They're both just a sequential data class. So here I can make an array of durations and values to describe a kind of arbitrary envelope shape. And then I can make a segmented envelope piece of data from that. And I can queue that. It says clarinet sample. That was wrong. Copy paste errors. That should be my envelope data, or my envelope. So you can queue parts of an envelope, attack and sustain, or the whole envelope, and then you can also change the rate of the envelope. So you could take an envelope and then play it at different rates and make it into an oscillator, an arbitrary waveform oscillator. So at some point, you want to get your data out of the synthesizer. So you can call synth render buffer. It'll take all the output from, there's a acyclic graph. Actually, it's a cyclic graph. But it'll do a pull through that graph and collect all the data and then render it into the stereo buffer. And then you can call audio bridge write suspending, which is from the other library, and you can hear your synthesized output. So you can also do, sort of Kotlin-y kind of things, like you can stick a lambda into this function evaluator, and then just embed that in the graph. So you can have an oscillator that then is processed by your lambda, which then goes through a filter or something like that. So you can just quickly and easily embed arbitrary functions into this modular synthesis graph. So I think we got 3 minutes. Yeah, I should just quickly. So this KSyn has a demo. I have to make sure I hit the. So you can, do things like play white noise, just random stream of values. There's a granular synthesis library, so you can change the density of things, change the variability of the ranges, change the duration so you can actually hear the tones or make them very sort of short. So this granular synthesis is a way to make sort of very kind of organic sound, like rain, wind, kind of even explosion kind of sounds. So there's lots of different weird stuff in here. Little Chebyshev song generator. So it's a lot of fun. A lot of fun to play with. So I got a couple more slides I have to hit. So in conclusion, you can make music, interactive music apps with Kotlin Compose. You can, if it's helpful to you, you can grab this audio bridge off of GitHub, the KSyn synthesizer off of GitHub, and there's the Praxinista app, as an example, is also on there. So these are all on my GitHub account, and you can access me through on Blue Sky or LinkedIn, and that's it. So thank you very much for coming.